Human amenability. Okay. All right. So I guess to start, this is joint work. Adam. I guess if it wasn't clear already, my handwriting's not the best. So if there's ever anything you can't read, just let me know. And so the goal for this talk is going to be to come up with a type of KPT correspondence in a very generic setting, right? So first, let's start off with some of the definitions from category theory. Basic stuff. So a category, usually I'll use the letter S, is a collection of objects which I'll use objects and arrows between objects. I won't go over the axiomatics because for the most part, it's just the axioms for function composition for how categories behave. And as for the arrows, as a notation, when I have objects A and B, I'm going to let SAB denote the arrows. This is a set of arrows from A to B. Okay. So you said we're gonna want it to just be a set. Yeah. What's interesting, I guess, is they can be in our setting. They can be really big sets. So in the usual context, all the sets that are generally worked with outside of this approximate setting, they're all finite. That's what's going to make this interesting, is that this one is generally. So I guess next definition is going to be that of directedness. Given a category S. This is sometimes called joint embedding in the case of we were working with finite substructures. So given a category S, we say S is directed. If it's directed in sort of a closed set. If for all pairs of objects A and B, I can find some object C such that A goes into C and B goes into C. I guess the picture. It's talking about categories, right? You can find a C like the fuzziest. And the reason why we're going to be wanting to work in this scenario where we have directed categories is because we're going to be wanting to talk about generic objects, right? And if you don't really have a directed category, there's no real there's no hope of getting a universal structure. This is a very necessary assumption for doing anything. That's this one. Yeah. Yeah, just the usual thing. Yeah. I didn't want to go into all the details here. I guess we're slowly getting to what it means for category to be specific. So another definition. So we have joint embedding or distractedness, and next we have amalgamation. Say category S as the amalgamation property. if whenever you have objects A, B, C, arrows F0, G0, A to C, A to B, and A to C, I can find a new object D and arrows F1, G1, such that we have this equality. Of course, category setting is good to talk about this because, of course, we can discuss the associated diagram for what we're saying here. So we're saying is we have A, and if we can embed into B, embed into C, this is F0, and this is G0, then I can find some D and some F1, some G1, and this diagram commutes. So the reason why these categories are relevant, why we're interested to begin with is, I guess, due to theorem of what's there. I don't know when this is from. Versailles theorem says that if S is the category, the directed category, although it wasn't written in this language, but finite models under embedding. So when I say embedding, I mean in the strict sense, right? So relationship preserved for function. Right? Directed model. We have the arrows we're talking about, and S is hereditarily closed. So it's closed under submodels and has the amalgamation property. Then there exists a unique optoautomorphism, or sorry, isomorphism. U, countable U, with the property that first, this U is universal. So if I look at all of its finite substructures, so H is all the finite substructures of U, this is equal to S, right? And two, U is ultra homogeneous. I.e., if you take two embeddings, let's call them F and H, from small structures into U, so this A is an object in S, then I could find an automorphism of U such that G composed with F is equal to H. Right?
You don't have to explicitly say that S is countable.
Let's see, American category finite. Yeah. You'll need. I think you'll need countable language. So yeah, it would. Yeah. Yeah. So I mean.
Well, often even up to isomorphism wouldn't be good enough. You is funny, you've got uncountable many equivalences. You're not going to get pH, VMX,
Oh yeah, yeah. So I mean, I guess so it's S, up to isomorphism class. Yeah. Yes. Yeah, so we'll assume, so in Versailles, yes, so we'll assume countable language, and then in our abstract setting, we'll start throwing more things out the window. Yeah. And I guess, so even like, so the KPT correspondence, which I'll explain next, it's done from looking at relational structures, countable language relational structures. And that's another thing we'll do, is we'll see that that's not necessarily needed. The only type of accountability we will need is when we want to talk about U without possibly having an actual U. So we're going to be talking about generic sequences. So they're going to be countable sequences. So in some sense, these categories will be countable in the sense that they're dominated by countably many things. But we'll get into that. Okay. So this, I guess, ultra homogeneity, it can be read in two ways, right? There are two equivalent notions for this. So there's this, which I think is nice from the perspective of when we talk about topological dynamics, right? So this idea is that this action of the automorphism group of U onto the embeddings from A into U for any A is transitive, right? So this is a transitive action. The other way to view it, I guess, in a more set theoretic way, is that any partial automorphism can extend to a global automorphism, which is the other way you view it. Okay. I guess, is there any questions so far? Yeah. 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 Okay. Countable language. Okay. Okay. So this theorem. States that, okay. If I guess I should also say, I should say some a little bit more. Actually, I shouldn't get to this theorem yet either. There's one more definition we need, but then we'll get to the theorem. Right? I need to mention what Ramsey means. So we call such F, or we call such S, per se. Just so that I don't have to say directed amalgamation hereditary closed the whole time. Okay. The next definition is finite structures with amalgamation, hereditary closed, all that. Yeah. Sorry? Yeah. Mm. All right. So let's see. So we say category S has the Ramsey property. Yeah. Yeah, and you need some extra condition about this existence of a Versailles sequence. So there has to be some type of countable domination. But I'll get into the definition of weak Versailles, which is what we'll be using, and then it'll be even more general. But for now, let's just stick with this so we can get to, I guess, the KPT correspondence as it was originally stated, and then move from there, or close to how it was originally stated. So we say category S has the Ramsey property. If for all objects A and B and K and omega. There exists some object C. That every coloring the arrows A to C into k many colors, there exists some arrow F from B to C such that the image is monochromatic. So in the structural sense, I think this is the cleanest to understand, right? So if you have two objects, A, B, usually A is small, B is a bit bigger. You can find some object C, which is larger than those, such that when you color the copies of A and C, you can find some copy of B and C, such that all the copies in A restricted to that copy are monochromatic, right? So this, I guess, the notation, or rather this is this. Sorry, less than or equal to 1, yeah. So I'm going to do less than or equal to just so that this makes sense, even if these things are completely unrelated, right? All right, just to make sure there's like some type of coherence here for I'm describing this. Yeah. I guess something I should note is, so in the classical settings, they're talking about substructures. But the theorems they want to work with, you want the substructures to be rigid anyways. So you want them to have trivial automorphism. You can check that in this definition, you're forced to have your objects be rigid. Right, so that's another thing to notice in the way I'm describing it here. Right. So, trivial automorphisms for each small object A, right? Because the idea is you could, if you color by automorphism class, right, and you can cook up bad colorings, and you definitely won't have this. So it's not so much, I guess, get rid of it. It's just if you have the Ramsey property, you need the automorphisms to be you need this to be original. You need trivial automorphisms because you can take coloring according to so the idea is okay. Yeah, it's Ramsey in the structural sense plus rigid, but in the yeah. Mhm. I guess now we discuss the correspondence, and then I get into the weakening that we're going to be looking at. I guess the big theorem we want to sort of emulate is this one. If S is for say category, so of relational models. So with all the associated baggage attached in the last, right? With ultra homogeneous U, right? Then the following are equivalent. So the first S has the Ramsey property. This is a statement about finite combinatorics, right? And then I guess what makes this theorem interesting is then you have the associated dynamical correspondence, right? U is extremely amenable. I'll state what this means. This is a very strong property, right? So this is, I guess another way to describe it is fixed point on compacta. So note that first OT U is a topological group with the topology of pointwise convergence, right? And this extremely amenable means whenever this group acts continuously on a compact space X, there is a fixed point. So there exists an X and X for all G, not U. This is very, very strong. The other way to phrase it is the universal minimal flow is trivial, is a single point, right? So there's only one minimal flow there. So it was questioned how many groups of this sort even existed. And what this theorem shows you is there's actually plenty of them, really. So for example, if you consider finite linear orders, right? This has the Ramsey property just by classical Ramsey theorem. And so the automorphism group of U, in this case, universal structure is the rationals by Cantor's theorem. That's extremely amenable. So whenever the automorphism group of the rationals acts on a compact space, there's a fixed point. Okay. So any questions about anything so far? Yeah. Yeah. I know in the classical setting, I think what they also describe, so what happens, one thing that does happen if you have this is if you have, this is extremely amenable, you could, in this setting, you can actually add a linear order on in a nice way that respects the, which respects the automorphisms, because the space of linear orders is a compact space, right? And so then when the automorphism group of U acts on it in a natural way, you can find a linear order that preserves automorphism, respects automorphism. And so then you can make the structures rigid. Right. So I guess the goal is we want to, again, so I've said it a couple of times now, we really want to weaken all the hypotheses here. And we also want to weaken this Ramsey property, right? Hmm? So a rigid means a trivial automorphism. So every small object has only identities automorphism. So like linear orders, right? Yeah. Yeah. Mhm. Yeah. Yes, yes, yeah. To be precise, this could be, yeah, exactly, yeah. Mhm. Yeah, yeah, linear order. Mhm. Okay.
So the conclusion, the equivalence is some extension of absolute transformation property,
Uh,
or just
so yeah, so okay, yeah. So the proper thing would be S has the Ramsey property up to expansion, I guess. Or some expansion of S has the Ramsey property would be in that classic setting.
The definition where you have just one automorphism implied if you've already added that linear order signature, you have a rigid structure. Right, but this doesn't satisfy that definition.
Oh yeah, in our classic Ramsey, if you allow finite sets with free, you don't. Yeah. So this will force that they're rigid. But I guess I'm just saying, I guess from how they defined things, you needed some extra assumption about rigidity because they weren't talking about it in this sense. This essentially will fix that. Okay. I guess any other questions about that or confusion? So one of the first things that we're going to weaken is so we want the same, we're going to get the same benefit. Yeah. I think it should be fine. We're gonna prove something, I guess, stronger anyway. So I guess we get to prove something. And we can come back and look. I think the way we're gonna find Ramsey will be a bit different, but you can transfer it into this setting and you get the same thing. I don't. But that's the entire lesson. So yeah, so the per se structure associated with that would just, yeah, so it would be omega with no. I was, yes, this, but I think the class in that sense, those are different. So it won't have that. Yeah, it won't have, very, yeah. I think we're getting, a weakening from something weakening of people, right? So yes, let's do a notation quick. This makes our lives easier. We have a category F. And alpha an arrow. We're going to let S alpha be. So this isn't an object now, this is an arrow. Right? This is going to be the set of things of the form. It's an arrow in something. SA prime. This is going to be the set of things this form. These are arrows that factor through alpha. So this is a subset of SA. S alpha. Yeah. The idea, yeah, so the idea is now in the first coordinate, I put the arrow. You call an arrow alpha amalgamable. Yeah. Familiar. Well, object zero. Now it factors through alpha. G0 now that factors through alpha. This F1 is just a B. 1 and 2, 0. Yeah. So this isn't, so in the case that alpha is just the identity error, to be amalgamable means you have the amalgamation property. Yes. To draw a little picture. The idea here is an arrow alpha is amalgamable. If whenever I have arrows that factor through these alpha, I can make this. Oh, so it's because yeah, because these are both factors now. So f, oh, yeah. Oh, yeah. They're both of the alpha. Okay. Another way it was initially written was you have to alpha up. Yeah, the only thing I don't like about that way of writing it, that's a fine way to write it, but this commutes, I mean this whole thing, right? The confusion comes from when you write it the other way, there's a fear that the inner square commutes, but the inner square might not. So when you write it like this, it moves that into. That's what it means for arrow to be amalgamable. You can discuss what it means to have the weak amalgamation. Hashtag weak amalgamation property. If every object A admits some A prime and some amalgamable element. The way, so I'll give an example of a category that has weak amalgamation but doesn't have amalgamation. So yeah, yeah, and thank you. So everything has some amalgamable arrow that runs out of it. So I guess as a brief example, this was in a note. I don't know when this was here, so I'm sorry about that. There's a note of Pabian. He says that this structure was given to him by Puset, I believe. So consider the rationals with the usual order. And now add, or consider now, consider this relation, this ternary relation. Where 3 points, we say RABC if and only if A is less than B and A is less than C and B is not equal to C. So we have this other relation that we got from the linear ordering relation. This structure is interesting. If you forget the linear order, only look at this ternary relation. This structure is pre-homogeneous. So I won't get into what this means. We'll get into science. We'll get into science post what this means in a second. But the idea is not every automorphism, not every partial automorphism can extend to a global automorphism, but partial automorphisms that are somehow well behaved. So the issue here with this ternary relation R is for finite substructures, the way they look or behave is they look like linear orders up to the last 2 points. And it has no idea how to relate these two things. And since it doesn't know how to relate these two things, it's possible that you can take an embedding into here that looks in the order of how they should behave. Right? And so then there's no hope of extending it. So this is the finite substructures of this are a classic example of something that has the weak amalgamation property. Right? You can see that the way the amalgamable arrows are the ones that tell me how these things relate. So embed this into something larger, right? So that now I know, like, okay, so now these things are in some order, and then I add some extra stuff on top. Right? This I can amalgamate with because it just comes down to amalgamating a linear order, right? But this I can't amalgamate. And in fact, I won't get into this at all, but maybe worthy of discussion later. Every such weak for say or weak amalgamation category with a weak amalgamation property can be turned into one with amalgamation property, kind of by cheating. The idea being is you use these amalgamable arrows as a way to say add this structure to the object. There's a way to do that, but it's not very intuitive for application purposes. So I haven't discussed what weak for say category will be. I will, but first, since it's been a while, we haven't done any proof. I'm gonna give one more definition for arrows, and then I'm gonna get into 2 useful lemmas. So this is going to be our definition for amalgamability. This is going to be our definition for Ramsey. So given an arrow alpha, we say alpha is Ramsey. If for all B objects in S, K and omega, and then here's the interesting part, and I'll discuss where this comes from. F subset S alpha B finite. So I have some special class, I'm quantifying over some class of finite embeddings, right? That factor through alpha, right? There exists some object C such that for all colorings of arrows that factor through alpha into C into K, there exists an arrow from B to C such that this is monochromatic. Not the whole thing, but only the arrows I care about in the finite set F. Right? So this is how we get rid of worrying about whether or not this is finite. So this is going to be so this is what we're going to be working with instead. We're working with these Ramsey arrows where we only care about fixing quantifying over these finite sets. So of course the C here can change depending on this finite set, but we only have to worry about this, right? Yeah. And I guess I should mention where this notion came from, or why we thought of this notion. Is because in the approximate setting, so when people were discussing approximate for say, so working with Banach spaces and such, they found an equivalence between extreme amenability and their approximate colorings or epsilon colorings, and then they equated that to something about finite subsets. So the idea here is you don't need control over everything to get this extreme amenability. You really need control over these finite subsets. or for every finite subset, you can get some control over it. I guess let's go through the first two. Doesn't really feel more of a lemma. First two lemmas that we'll use later. This is rather nice because it tells you in some sense that if you're interested in Ramsey properties for structures, you're going to need Forsay structures, or you're going to be needing to work in the Forsay setting. So let me write the theorem. So suppose S is directed. We're going to need this directedness. If alpha is Ramsey, so if we have a Ramsey arrow, then alpha is amalgam. So if you go to the concrete setting, what does this tell you? Well, this tells you being Ramsey, having the Ramsey property is equivalent in that setting to the identity arrow being Ramsey. So if the identity arrow is, if you have the Ramsey property, the identity arrow is Ramsey, and by this lemma, identity arrow is amalgam. So you have the amalgamation property if you have the Ramsey property. So somehow this is the only setting you really want to work in. And of course you want directed because you want to talk about some type of universal structures anyway. Right? So of course, we're going to start with alpha Ramsey. And we want to show it's amalgamable. So take F0, some arrow that factors through alpha into B, and some G0 that factors from alpha into C. Since S is direct, there is some D that embeds both C and B, right? Call them, alpha 0. 0 yes. D maybe small diagram. And let's ignore the arrow up. You have these arrows that factor through alpha, F0 and F1. I'm finding, so this is A, this is B, this is B. So I'm finding some structure D that both embed into it. But this doesn't necessarily mean because they both embed doesn't mean. But I'm going to, now that I know that they both come into something, I can use the Ramsey property on this thing and somehow cook up a coloring that will give me this is an so oh, but you want me to keep, okay, I can keep. Call an arrow amalgamable if whenever you take some BC and some arrows from alpha to B and alpha like alpha. So for any type, so I'm trying to search amalgam and like take it. Yeah. You want me to move it? I guess from the definition of Ramsey, I need a what? So now I also need to consider quantum. I need a k, right? And I need some finite f, right? So the f I'm going to pick is going to be, let's make sure delta 0 composed of f0, gamma 0 composed of g0. So this is a good choice of f, right? And for k, I'm going to set k essentially equal to 2. So find v that works for, so these are just some arrows. Yeah. Find v that works for f and 2. Right. F, I should say the b, right, or d, right? F, d, and 2. Although I guess maybe d is clear from the F term. Okay. So this means that for every coloring of the alpha arrows that factor through here, you can find some arrow into v from d, such that I get that it's monochromatic when I compose on the left with that, right? That's what the Ramsey definition is. So I need to cook a coloring and hope that this somehow helps me. So consider the following coloring. Color of H, say, equals 1, if and only if H equals E composed with delta 0 composed with F0 for some E in S D. So in other words, you get color 1 if you, the color 1 is sort of like the indicator of this one, right? If you can be written in this form, then you color 1 for some E. Maybe I should say, yeah, let's look for some E. Now, by the Ramsey property, I know that there exists some E1 from D into V, such that E1 composed with, or delta 0 composed with F0, E1 composed with gamma 0 composed with G0 is monochromatic, or is phi monochromatic. So these take on one color. Now notice that by the way I've defined my coloring, this has color 1, right? But since this has color 1, this has color 1. So there exists some E such that E1 composed with gamma 0 composed with G0 equals E composed with delta 0 composed with F0. Okay, well then let this be G1 and let this be F1. And I amalgamate it. Right? So if an arrow is Ramsey, then it's not. Right, so I'll push this up as well. I guess another lemma, this one I'll try to go through a bit quicker. We can prove the main resolve. this one's also nice because it says something about the cofinality of being Ramsey. Let me explain what I mean. So suppose alpha and S A prime, beta and A prime B. If alpha or beta is Ramsey, beta composes alpha is Ramsey. So if you take a Ramsey arrow and you compose to the left, it's Ramsey. If you take a Ramsey arrow and you compose to the right, it's Ramsey. Okay. So I don't think you need directedness for this. Yeah. If this one, I don't think you need directedness. So why is this true? So, well, first, so I guess maybe it's just a sketch. Here's the idea. So analyze this set for 1 second. Into some, I guess we have B defined here. So in some C, right? So these are arrows that factor through alpha and then factor through alpha composed with beta. So these are arrows that kind of look like this. Well, then they look like that. This is a subset of this. So when alpha is Ramsey, it's immediate. You have a finite subset here. It's also a finite subset here. Take a coloring here, extend it however you like the coloring here. Find the thing that makes it monochromatic, right? And then on the other hand, so that's what happens if alpha is Ramsey. Oh, I guess maybe let's leave that here. On the other hand, if you want to show that this is Ramsey, right? So if you want to show beta is Ramsey, if you want to show that this composition is, sorry, you know beta is Ramsey, and you take a finite subset here, so then notice that this F is equal to F prime composed with alpha, or some F prime, it's a subset of this, right? It's going the other way. In this case, when you have your coloring, there's a natural way to push it to a coloring here by just tacking on alpha, right? Or there's a natural way to go about doing this as well, right? So I'll leave that so that so we can get to the main theorem. Are there any questions, I guess, about it? Okay. So I guess let's go to sequences and cones, and then we can do the main theorem. So given category S, a sequence is a pair of objects and morphisms. I should use them. So are objects in S, and UMN are morphisms from M to N. And I guess some things to note are UNN or UMM should be the identity. So we're trying to define essentially like what you would define for some type of directed limit or directed sequence, right? And then you have this condition that if if I travel from K to M, and then I travel from M to N, this is the same as if I traveled from K to M, right? So you have these conditions. So this is what a sequence is, right? In a category, right? And so this is going to get into, so this is what we need to define what it means for a category to be weak for say. So if, yeah. Yeah, so I guess one thing that some people do in this field is due to the nature of how category theory is very general, you can talk about inverse limits by just defining composition to be the reverse on your category. Yeah, but I guess from the its classical sense, yeah, it's directed. Yeah. Okay, I should state the order of these. Thank you. Yeah. Yeah. So it's yeah. Weak for say sequence. In a category S. Is a sequence with the following two properties. The first is easy enough. For every object, and this relates to, in some sense, that countability that was talked about before. So for every object, there exists some M such that we embed into. So the sequence is somehow universal over the category. So that's going to take care of the countability criterion that you usually want to worry about. And the next is a little more challenging. So for all M, there exists an N larger than M such that for every, I guess let's call it A. I'll try to draw a picture with this too. Object of S and F, some arrow from the bigger thing, from let's see. So yes, into A. There exists a bigger N and a beta from A into UN such that beta composed with alpha, or composed with F, composed with UMN equals UM big N. So maybe I'll draw a picture here. So we have UM here. We have some N larger. Whenever I leave F, right? Yes, it's getting a little messy. Whenever I leave the sequence, there's a way back in. So this is relating to, in some sense, this should look like weak amalgamation or amalgamable errors. In fact, with this property, you have that for every M, there's an N large enough such that UMN is amalgamable, right? And so then a category we say is weak for say if it admits a weak for say sequence. So, so the idea is I'm not just looking at just F. I'm looking at really F composed with the UM. Maybe another way to write it. So this has the same issue as I discussed before. So maybe another way to look at it is something like this. So it's because that would be what you're describing is actually what they call a Frisé sequence. So this is more like this. And then we go along into some A. And that's F. Then we can move back. So I guess trapezoid might be a better picture. Right? The idea is that this arrow is being composed here. Okay, so we say S is weak for say if there exists a weak for say sequence. Yeah. So yeah, in that case it would be yeah, exactly. Okay. I guess let's get into the last thing we need and then okay. Sorry, there's two more definitions. This one and then one more. And then we can get into the main proof. Okay. So now that we have a weak for say sequence, I want to discuss I want to talk about some universal structure. So in general, let's from this point forward fix S and L categories. S subcategory, not necessarily full subcategory of L. What this is trying to encapsulate or simulate is S is small and L is large / limited, right? Just because I want to talk about the limit, but I don't want to just talk about the sequence, or I want to relate the two, right? So, cone. So a cone is, okay, so a cone is tuple UMN, infinity. Just draw this quick. So a cone is as a sequence, and then some special limiting object U, and then you're embedding arrows into U. Okay, that's a cone. Weak for say, so you don't have every arrow is amalgamable because then you'd have amalgamation. But what you do have is you have that every object admits an amalgamable arrow. And the way you do that first is, way you can do this is by essentially you go into the sequence using universality, and then you kind of work around from there. Try to find it from there. Because those UMN are for a large enough n. The idea. Yeah. Yeah. Okay. So a cone is matching if satisfies these 4 conditions. And the last one is the first is for every arrow into U, let me actually make sure I'm not writing this incorrectly. Yes. There is an N. Bigger than M. F prime. It goes from UM to UN. F is equal to UN conclusion composed with F prime. So let's explain this. What this is saying is if you have an arrow from your from a small thing into your limiting structure, then there's an arrow between small things that encapsulates that. So it's just maybe an idea in classic settings. So if you have an embedding of an object into a bigger object, well, really that's just an embedding from your object into some larger fragment, or some larger but still finite fragment of your codomain. That's essentially what this is saying, right? Next, if F0 and F1 are such that these are equal, there exists an N large such that they're equal there. So similar to, think about again, maybe in the classic model setting, what this is saying is if I have 2 arrows that I take their inclusion into the bigger structure, after some finite amount of time, I've encapsulated all the information I need for the embedding, right? So these are sort of like, I guess, codomain type control, if you think in the classic model setting. So this will hold in the classic model embedding setting. This one, back and forth, a picture is best here, and then I'll describe just what's relevant for it. So what back and forth tells us is if you have a sequence of arrows that go back and forth, then this back and forth property is witnessed by some automorphism. A corollary to this is if, and this is what we'll be using, if UMN is amalgamable, then this action is transitive. So you have this pre-homogeneity, right? And in the last condition, this is easy enough. So this one, okay, yes. So if you have 2 arrows here, say F and H, there's an automorphism that makes them equal. The only difference here now, I guess, compared to the classic precise setting, is they're factoring through some bound. Okay. The last is the Hausdorff condition is for all F in the automorphism group. That's not the identity. There exists an N such that F composed with UN infinity is not equal to UN. In other words, if you don't fix the structure, then after a finite amount of time, I see you don't fix the structure, right? So these conditions, or especially this last one, they give rise to an interesting topology on the automorphism group. Mhm. Mhm. Yeah. These are an S and these are an L. Thank you. So. The automorphism group of U is a topological group with basis identity not even. This is essentially trying to mimic pointwise convergence topology. I guess I'm giving it this topology. I'm declaring it. So I guess some properties of this topology. So Vn form subgroup, your subgroup at the identity. So just like in the classical setting, this is a non-Archimedean group. Hausdorff condition guarantees that this topology is Hausdorff. And you have that it is completely metrizable as well. You need back and forth in the factor conditions to show that. Metrizable is easy enough, but it's also completely metrizable. I guess also aside, it's interesting when these are finite or countable actually, then by these conditions, this is actually a Polish group. Or in particular, it's a subgroup of S infinity. We don't need it to be, but if it is, then it is a subgroup.
In some way, we're a match for every time. Like, we've got to go back to so you're matching to be given the best.
Oh, are you saying like, can I get something smaller?
Yeah, if you've got like a cone.
I don't know. I mean, in most cases, the thing you want to do is the obvious thing, right? Like for example, if you're working with structures, you really do just take a limit, right?
Yeah.
And that's when what your DU you're going to be interested in. But here it works for anything. Okay. Okay. A lot of setups, but we're finally here in the finish line. So given a matching cone, we say an arrow alpha in S is, these are terrible names, so we just call them WA and WB. WA is weak finitary big Ramsey property A, and this is a weak finitary big Ramsey property B. And they mimic the natural way in which you use compactness to get Ramsey's theorem for finite structures from infinite one. So the idea is if we're all K and omega, F subset L alpha U finite, there exists an automorphism, and I guess coloring, sorry, and phi coloring. There exists an automorphism such that this is monochromatic. WB, the same thing, but instead of requiring an automorphism, we just require an endomorphism. So mapping from U into itself. So WA implies WB. As an automorphism as an endomorphism. Right. So I'll do just one direction of this proof. And then, well, there's three directions. I've technically already done, one's easy. And then I'll discuss the main result and why it's true. Right. Following are equivalent. Alpha is Ramsey. So for we have a matching code in this setup. Alpha satisfies WA, and alpha satisfies WB. So 2 implies 3 is easy, right? It's just straight definition, straight from definition. We'll do 3 implies 1. 1 implies 2 is a lot longer. Don't really have time for it and the final statement. But I'll do 3 implies 1, which also looks exactly like I mentioned how one goes about proving finite Ramsey theorem from the classic finite Ramsey theorem from the infinite one. It goes through more or less all the same steps. Yes, any questions so far? Maybe should have kept the factorization condition. Thanks. Okay. So let's do 3 implies 1. So we're going to suppose alpha satisfies WB, and we want to show that alpha is Ramsey. So suppose alpha is not Ramsey. So there is some object B, right? K and omega, and finite F that are witness to alpha not Ramsey. Witnessing this. Oh, well, it's not quite. We also need bad colorings, right? And we can take the colorings, since the UN, the sequence UN is universal of these objects. We can take a sequence. This makes sense, at least for cofinely many n. So these colorings are such that I can't find anything to make these monochromatic, right? Can't find any map from B into UN that makes these monochromatic. So then what do we do? For each F in alpha U that exists in M in omega and F hat such that F is equal to inclusion composed with this F hat. This was the factorization condition, right? Let delta M of F, or delta N of F equal UMN opposed with F, N greater than or equal to N. Right? So these are like the nth approximations of F, right? Approximations of the function. It's also take P non-principal ultrafilter. On omega. So remember, I'm assuming WB. So I want to create a coloring of the entire structure, or embeddings of the entire structure. So what am I going to do? Oh, do the classic thing. So you just take the limit. So this makes sense for cofinally many n. So this makes sense, right? Takes on finally many values. So this thing, everything here makes sense. Well defined. Right. So now we have our coloring. And now we're going to use WB for the right choice of F. Right? So what F are we going to use? This, make sure get through this. Okay. So this is finite. So there exists N0 sorry. So find N0 such that there is some E0 from B into UN0. Right? And the F I'm going to consider then is F prime equal to U N0 really composed with E0 composed with S. Right? Because these are maps into B. So I want to get back into the some UN0 and then from there go into these maps. Right? There exists some endomorphism such that B is monochromatic with respect to on E composed with UN0 composed with E0 composed with S. So for this map here, by our now deleted factorization, I can find some arrow E prime and some N, I guess maybe N prime, such that E composed with UN0 composed with E0 is equal to UN prime composed with E prime. And now it's just a bunch of algebra. So the idea is this set is monochromatic with respect to C. So there is some color class which appears really often. Here's what it is. And then, yes, I didn't get to the main result, but essentially these equivalent, condition WA and WB are equivalent to extreme amenability through finite oscillations together. This WB looks exactly like finite oscillations together. The idea now is for F and F, we have that En of and close it B prime, close it back. This is equal to infinity composed with E prime composed with F. The nth approximation of this map. Right? So by the way, I've defined E prime is the nth approximation of E composed with UM infinity. I guess some zeros. Anyway, composed with E0 composed with F. Right. So the idea is for each F, there is some n large enough, ultrafilter many n large enough for which this is true. So for each F, so such that this is equal to J, where I guess this the set of n for which this happens, AF, is in our ultrafilter. Yes, sorry. So EN, and then so yeah, and so then it will be the limit of this, which is just so the limit of this is phi. To be this, because the limit is just this thing. It'll be E composed with this, composed with this, composed with that. By the way, it's defined. Not principal. Yeah. And so since these are finite, right, there exists some n and this. And what you'll see for this n, for all F and F, En UM n composed with E prime composed with F equals J, which is a contradiction to it not being monochromatic. The idea is I can find some n large enough so that this is a monochromatic. This is mimicking exactly the compactness argument for classic Ramsey theorem on omega. Sorry, I got a little botched at the end. Yeah, so okay, so with so the idea Yes, okay, so the idea is you have I'll write it out, I guess. Yeah, so the following are equivalent for a matching phone. In S. So one is S has the Ramsey property or the weak Ramsey property. So every object emits a weak Ramsey arrow. And the last is thought view is extremely amenable. That was exactly what one would expect. In the case that the set of morphisms is infinite, it's completely new because it may not be a subset of S infinity. It gives you new more in the sense that you can create groups you might not otherwise be able to simply create from structures. Yeah. So that one it does, but it's not interesting because it ends up being the same one as the rationals. Right? Yeah. Well, I guess one weird example we did look at that's not like in the same setting at all is if you consider a category with a single point, so just an object, like a single object, and then a monoid acting, you can create bizarre sequences of elements from the monoid, and somehow you can there's some type of group related to that. It's bizarre. That's one example, and the other was we considered strong trees under strong embeddings. So we tried to get a more structural type of Millikan's theorem. We didn't, but we did for weak tree embeddings. Those categories don't have the automation type, but they have weak lands. So it's a little tricky. Because technically speaking, it's more like whenever the morphisms are finite, like in our or countable, like in our setting, they will be this group will end up being a subgroup of S infinity, right? So there is a classical precise structure. It's just that usually the way you get that precise structure is by looking at orbits. So it's not clean. It's not a clean way to look at it. You know, like I guess maybe what I think about it is, so if you take an automorphism group of S, if you take a subgroup of close subgroup of S infinity, it's associated with the same structure, right? But it's not always, but the way you describe that structure is create infinitely many relations by looking at the orbits on n powers. So that structure is just not conductive to finding this stuff to be. So it gives you a more broad way to try to find and classify those ones and other ones. But that's still kind of open. Curious if there are categories of these arrows are separate. That's something to do. That's the non-point. I guess. Sorry. Discuss that with more detail. Maximum what sense? Oh, I see. You mean like in the sense that you can enlarge it to infinity, but would you not use it? I don't know. Oh, so they sorry. No, yes, I didn't say that. So I meant like they're new in terms of characterizing. Like you might get something that as far as characterizing. Yeah. Yes, so I guess, so yeah, so I made a very brief mention. Basically, for any category S that's weak per se, you can construct a new category, we do like S up arrow, that ends up being the same. And the idea is the objects in this are no longer just objects, but they're objects paired with amalgamable arrows. And now you ask or request for the arrows between these objects to factor through that arrow. So it's a very cheap way of doing it. The idea being is that, I guess in the model setting, once you have an amalgamable arrow and you know, and you know what to embed it into, that structure is added back as a substring. That's the idea. Yeah, yeah, yeah. Yeah, that's exactly what it's saying. Any other question? All right, thank you.
Is that what, is it out?
Hmm?
Is this what out in
Yeah,
some?
yeah.
I'll give it a read.
It's very long,
Oh, how long is it?
60 pages.
Oh,
This is essentially 40.
okay. Where does the bulk of the word count come from?
This proof.
Literally.
Oh, not just this proof, but like this setup. The setup is long. It's like 20 pages of setup, as you saw. There's a lot of definitions. Because you need to get everything in a very general context, but you also need to know what exactly it is you're working with.
Yeah, because I guess
Yeah.
not everyone has the same background.